Okay. Let me go ahead and share my screen and we will jump right in, everybody. Bam. Okay, welcome to Exploring Pinecone's Sparse-Dense Index. Say that 10 times. My name is Amanda Wagner. I am the Senior Community Manager here at Pinecone, and we are absolutely thrilled to have you joining us today. For those of you who are unfamiliar, which I assume a good amount of you are attending this event, Pinecone is a vector database that makes it easy to build high-performance vector search applications. Now, before we jump into the event, we do have a few housekeeping rules. We ask that number one, please use the chat for chat. Feel free to introduce yourself, say hello. And when you do have a question, we ask that you put them in the Q&A portion of the Zoom. So questions, Q&A portion, chat. If you miss something, no worries. This event is being recorded and we will share after the event. So you can watch it as many times as you'd like. If you have questions after the event, you can reach out to me personally at amanda@pinecone.io, and I will serve as your inquiry liaison to make sure we get your questions answered. Along with that recording, we send out a post-event survey. Your feedback is super valuable, so please take 30 seconds and let us know what you think. Now, without further ado, I'm going to turn it over to James Briggs, who's going to get us started today. James, take it away.
Thanks, Amanda. Okay, so I will just share my screen quickly. One moment. Okay. So I think we should be okay. Yeah. Okay. Cool. I'll assume that you can see my screen. So we're going to, like we already mentioned, we're going to go through the new Sparse-Dense index in Pinecone, which is this slide. And I was going to, before we even start with the Sparse-Dense index, I kind of want to give a little bit of an introduction to basically everything you need to know in order to understand what is so special about the Sparse-Dense index. So we'll start at the very top, which is vectors in retrieval. So in information retrieval, for a long time, there has been the approach of retrieving information using vectors. So essentially, what you're doing there is you're representing information in some sort of vector format, and then you're retrieving relevant information based on a search query or a recommendation or something else using another vector that you've created based on that query. I was something to go into slideshow. Right. So traditionally, we use what was called a tradition, or this a little while back, there was a bag of words methods for this. So we can think of the bag of words methods as, imagine you have like a sentence here, you split the sentence into all of these individual chunks of words in this case, and you put them into a bag. From this bag, you create your vector. So each one of these items in this vector actually is each position correlates to a particular word, right? And this here that you can see is kind of, it's not a good representation of, but that is what a sparse vector might look like. Now, in reality, your sparse vector will have many more zeros than that. and probably look a little more like this. So you'd have potentially thousands, tens of thousands, even more values within your sparse vector. Most of them are going to be zero, and that's why it's called sparse vector. Now, there's a few good things about sparse vectors. They're quite efficient. They have a good baseline performance. You don't need to fine tune like neural network models in order to get that good baseline performance. It's pretty interpretable, like you know why there's values within your sparse vector because obviously a word appeared. And you also have exact term matching, which is essentially, imagine in your search query, you have a particular, very specific word. You will be able to exactly match that word to the same word in a set of documents that are stored in a database somewhere. Now, there are some issues with sparse vectors. A big one there is that like human nature doesn't really work well with them, right? So we have this query in this document, right? This document is very specific to our query at the top here, right? But if we're going with sparse vectors, we're kind of relying on there being an overlap in the terms between these two items. And in this example, the only overlap is the word Indonesia. Although we're saying, large monkeys and orangutans are obviously pretty large monkeys, come from, is overlaps with native jungles and rainforests. There's a lot of overlap in meaning there, but there's not really any overlap in the actual terms. So what we would describe this as is the vocabulary mismatch problem, which is the vocabulary in the query and the document are different. And that's just because there's a lot of different ways to say the same thing in human language. So that's one of the big problems. There's also other problems. It's hard to, for example, improve the performance of your sparse vector retrieval because you can't train a neural network or anything like that. So, there are a few issues. And to some degree, dense vectors are supposed to solve those issues. So with dense vectors, we're searching based more on meaning than term matching, like you saw before. So what I mean by that is you're going to take a neural network model, like a transform model. And this transform model or something that's been trained on a ton of language. And based on all the language that it's seen, it identifies patterns. And it identifies that one particular sentence or paragraph is similar to another one. And that it is dissimilar to something else. So based on that, it essentially learns like a vector representation of language that we can, so that we can encode two sentences that maybe don't have the same meaning, don't have the same terms in them. But if they have a similar meaning, they will be close together within that vector space. So if we do go with that approach, we are able to search based on meaning, which arguably is a better way of searching for humans because we kind of think of everything in these sort of abstract conceptual ways rather than term matching. And because we're using these neural networks, which can learn very abstract patterns and everything, we can outperform sparse retrieval methods if we do fine tuning, which is if we train the model on a particular data set, which is specific to our different use cases, right? So, for example, maybe you have a load of medical documents. Those medical documents have very specific medical terminology inside them. So in that case, a dense embedding model, you'd have to fine tune it on that type of language. And then there's also multimodality, which we'll see later on, but you can think of multimodality as searching across different types of media. So like you can search from text to image, or across audio and video and all these different things, which is pretty cool. But there are definitely a few issues with dense vectors as well. So I mentioned before, you need to train these dense embedding models in order to match sparse performance. So sparse embedding models, they have a good baseline performance. And in order to surpass that with the dense embedding model, you have to train the model in most cases. They don't generalize well. So I can mention that the medical example. If you train a model on a ton of English language data, it doesn't necessarily mean that it's going to just perform well on all English documents, particularly if you have niche terminology, like in the case of the medical domain. And the same applies to different languages. If you're going like to another language that maybe doesn't have as many training resources online for, that can be pretty difficult. There's also no exact match. So you're searching based on meaning, which means that that's great, but we lose out on the ability to search for exact terms. And it's also not easily interpretable. Like you look at this vector here, and there's not really a way of interpreting this. The neural network, like a black box, it's done something to create this, but it's kind of hard to understand why all the time. All right, so there's kind of two separate paradigms in search that we just discussed, which is sparse vector search and dense vector search. So can we, would there be a way to use these together? There have been some attempts to do this. So a typical approach is to use what we would call a two-stage retrieval system. So in this scenario, what we have is we have our user query that goes into a sparse retrieval. So this is going to generate our sparse embeddings. That goes to a database where we have all of these documents that are being encoded into sparse vectors. And because sparse retrieval methods are pretty efficient, that can be very big. We can store a lot of data in there, and we can retrieve, let's say, like the top 100 most similar items to our sparse query vector over here. So we retrieve the top 100 documents there, and then we pass them into our dense re-ranker. Now, the dense re-ranker is slower. So what this will do is, based on those top 100 documents, it's going to re-rank them based on their semantic meaning. And that's quite a good approach. And it works well with this dense re-ranker because dense re-ranker is slower, and we only have like 100 items here. So we're not searching through the entire database with the dense re-ranker. So that avoids this process being too slow. So it works well, I think, for the same reasons I just stated, actually. So yeah, we search through the full set of documents with a faster sparse model, and then we re-rank on a smaller set of documents with a slow dense model. But again, it's not perfect. So 2 stages can actually be slower than a single stage that uses approximate nearest neighbor search. And that is approximate nearest neighbor search using dense vectors. And 2 stages can be more complex. So there's obviously going to be more engineering challenges. And performance entirely relies on the first stage returning good results. So, if you are wanting to search based on meaning and get good results, it can get you there, possibly, but you're relying on that meaningful result being returned through a sparse retriever, which is not searching based on meaning, it's searching based purely on term matching. So you really are relying on that sparse retriever, giving some decent results. Otherwise, yeah, the dense re-ranker doesn't have anything to work with, and you're not going to get anything decent from that. So one other thing, actually, one other thing that I actually missed on the benefits, I should just mention it very quickly, is obviously in some cases, maybe you have a system which, like a sparse retrieval system, and maybe that feeds into multiple other systems. So the two-stage retrieval in that case can be quite useful. Like maybe you have a dense re-ranker for one task, a dense re-ranker for another task, and so on. So that's just another pro for these types of systems. Okay, cool. So the other option is single-stage retrieval. So this is, as it says here, it's where you have a retrieval system that just has one stage to it. So this can look differently depending on what you're going for. So you could just have like a sparse retrieval system. Okay, so in here you'd have your sparse embedding model or retrieval model, and in here you'd have sparse vectors. And then you would get your results, and you're going to get results based on that exact pair matching, whatever else. Or you can have a dense embedding model in here, or dense vectors over here, and you're going to be searching based more on the meaning. So the one issue we have here is, you know, I just said we can either search with dense or we can search with sparse. We can't do both because single stage doesn't support hybrid, or at least single stage didn't support hybrid until we have Pinecone's Sparse-Dense index. So what Pinecone is doing is we have what we call a single stage sparse-dense retrieval index or retrieval system. So imagine you have your query, right? It can be text, it can be images, it can be both. It could be text and images, and we'll see an example of that pretty soon. You would take them into a dense embedding model, or also into a sparse embedding model. You get your sparse vector over here, your dense vector on top, and then you would pass that into Pinecone to perform your query, and you get a load of matches. Now, those matches are based on both your sparse and your dense vectors. So it's not just one or the other, it's on both. And it's all wrapped into a single stage of retrieval. So what that kind of looks like is, so this is when you're populating your index, sorry. So this is when you're querying your index, when you're performing query. This is when you're populating it. It's pretty much the same process. So when you're populating your index, you have your database or your documents all over here on the left, process them through your two models. You put them both together in your Pinecone upsert, and then they go through the process to the sparse-dense index. Now, what we'll do is, just to give you a bit of grounding on what that actually looks like, is we'll go through a demo. So in this demo, it's actually going to be a few different things, just to kind of give an example of how you can use this sort of method. So we're going to actually have kind of like an e-commerce example. We're going to have both images that are paired with text. Right, so that's kind of what I'm trying to represent over here. So we'll have an image of some guy wearing jeans, and then it will say like French Connection, which is a brand, dark blue men's jeans. And what we'll do is we'll take those images, process them through a dense embedding model that can handle text and images, but we're just going to be processing the images called a clip. Then we're going to take the text, process it through a sparse embedding model, BM25, which is kind of like the traditional, most popular method. Put both of those together to create our Sparse-Dense vectors, and then we'll pass those over to Pinecone's Sparse-Dense index. Okay, so let me just find that notebook quickly. Okay, that's very useful. 1 moment. Okay, give me a second while I just reconnect this. Okay, sorry, I'm going to share my screen again. Right, so what we have here is the notebook. You can also follow along with this. There will be a link in these slides when they get shared to you after this, and you can also just find it. We have this Pinecone examples repo. If you go to examples, search, hybrid search, go to e-commerce search, it will be in there. And there's also a few other examples here if you'd like to take a look at those. So yeah, let's go through this. So the first thing that we have at the top here is a few libraries that we're going to be using. Transformers, extension transformers for handling the embeddings. We have Pinecone, obviously, for vector database. We have Hugging Face data sets, which is where we are getting the e-commerce data set from. Okay, second. Sure. So we load data sets. So this is from Asterisk. So he has put together this data set here, which is basically it's just a set of images, or the part that we care the most about is we have these images, just very small images of some fashion items. And then within that data set, we also have these other items. So we have a little description here. Now, we're not just going to rely on that description. We're also going to pull in other relevant information. So we have like gender, the type of clothing that it is, all these other different things. So go through, this is, here we're just taking care of the tokenization or the embedding of everything. So the BM25 embedding model here, which you can kind of see a little bit of what's going on here. So tokenizing, so it's breaking the description out into these little words, and then it's going to tokenize based on that. So you will end up getting something that looks like this, right? So before I showed you the sparse embedding model, and it was like just full of zeros, and then there's like a occasional number in there. This is the same thing, right? But we just reformatted it in a more efficient way. So we know, let's say we have all these zeros, and then we know at position 3,836 there's a number, which is this number, right? And then at position 10,000, so on, we have this number. There's no point in us storing the full vector of all those zeros. We can just store it as a dictionary where we're mapping those values to the positions that they are within. So that's all we're doing here. That's why this doesn't look like a vector as such, but more in this sort of dictionary format. And this is the same format that Pinecone also consumes for sparse vectors. Right, so there's sparse vectors. For the dense vector, we use, it's a clip model, and we're going through the sentence transformers library to get that. It's actually really simple. So we just initialize the model, we come down here, and we encode some text, right? It's really simple. What we'll get is this 512 dimensional dense vector, and that will be full of values. So let me just make sure I don't need to run anything else. I think I might need to run this quickly. Okay, and this. Right, cool. I hope that's everything. And maybe this as well. Okay, cool. And let's go down to here. So here is the upsert code. So I'm not going to describe it too heavily. Kind of go through that. There's comments everywhere. But essentially, we're just going through the whole data set here, and we are embedding everything, creating our sparse and dense vectors, and processing those and adding all those into Pinecone, which I've already done. It doesn't take that long, but I don't think you're going to wait a few minutes while that processes. So let's run this and see if it's going to run, or if I need to, or if I've missed something. Yeah, something. Check up here. Okay, I'll just run this quickly. Okay. Right. So I think that will take a moment to run. So when you're using BM25, you basically have to train the model on your data set, or let it see your data. So that was a bit I missed there, I think. Let's come to here. Okay, cool. So what we're doing here, just to explain it, we have a query, this dark blue French connection genes for men. We create our sparse vector, our dense vector, and then we query. So we're querying Pinecone here. We're saying I want to return the top 14 most relevant items. We include metadata because that contains relevant information, like textual information that we as humans can read, not just the vectors. And then what we can do is, based on our data set, just return those JPEG images. So we come down to here, just so we can display everything, and run this, right? So these are the results for whatever that query was, dark blue French connection genes for men, right? So we can see that looks pretty accurate, although we'll take a look in a moment and maybe we'll figure out if that is accurate in terms of, are these actually French connection or not. Another thing I kind of want to show you is that we have this hybrid scale function, which allows us to kind of prioritize whether we want to do more sparse or we want to do more dense search. So that can be quite interesting. So if we go for 0, that means we're doing a pure sparse search. So let's do that and let's take a look at the results. So we can see that, yeah, it looks, we have all these men's genes, and then we have a couple of women's genes in here. So, why is that? Well, if we're doing pure sparse, you saw before, that means that we are searching based on terms, right? So here you can see, okay, this contains French connection, contains men, blue, and genes, right? So that's a pretty good match. The next best thing to that, however, is this, because it contains blue genes and French connection, even though it's for women, right? So we are kind of surfacing those before, maybe we would actually prefer to surface French connection men's genes that are a navy color, because it's pretty much blue. So this is where, okay, maybe the more meaningful dense vector search would be useful. So we can run that, and what we will get, this is like pure dense, right? So we're searching based purely on the dense vector representations of the images, and they look good. I think it's like dark blue, they're all men's genes. But then if we come down, we realize, okay, that's not actually right round. We have locomotive men, or is it maybe locomotive, the brand? We do have French connection there, but it's not actually what we're looking for. So maybe we can do a bit of both. All right, so we start alpha to 0.05. So this is mostly sparse with a little bit of dense. And we get really good results kind of like pretty quickly. So you can see here, we get French connection, men's genes, that blue, and then we have locomotive genes, which not ideal, but it's better than, I think, getting women's genes if you're searching for men's genes. And, you know, maybe looks-wise, they're very similar. And then we can obviously fine-tune that. We can adjust the alpha parameter to go more dense, go more sparse, you know, whatever it is you're going for. So let's try a few more. So we have small beige handbag for women. All right, see what that looks like. So this is, we're going pure sparse vector search right now. And like, they're definitely all small handbags for women, but I don't think any of them are beige. So it's not ideal. Let's see what happens if we add in a little bit of dense in there. So the dense images, and you see that straight away we get like just beige, which is pretty good. Even though we've only added a very small amount of the dense vector search in there, that kind of fixes what we were searching for straight away. So that's pretty cool. And then if we can have a look at the image, and not the image, the text here as well. You see that we have women, beige handbags, so that's where the sparse part of it's coming in. Okay, that's cool. And then if we do like pure dense, because, you know, maybe we just need to do a dense image search here, you know, what do we get? We get beige, right? But they're not necessarily handbags, and they're not necessarily all that small looking. So like this is, I think we'd call it a purse, another purse, right? So the color is good, but the actual, what we're seeing here isn't good. And that's just a limitation of the dense embedding model. It's kind of seeing, you know, handbag and purse as being pretty much the same thing. Cool. So we can try something a little more interesting. So we're going to start with this. This image here. So I said before we can do multimodal search. That means we can search from text to image, but it also means we can search image to image or image to text. So what we would do is we'll take this this image here. Let me just double check what we we are actually doing. Okay, so we're taking this image. We're using that to create our dense vector. Then we're also, and then we have this text query that we're using to create the sparse vector, right? So we're kind of like we're kind of mixing both of those together. So you can imagine like in an e-commerce setting, maybe you see something that you like, but it's not really, maybe it's the wrong color or something. So maybe you select that image and you say, can I have this, but in like purple and maybe like a longer or something like this. But that's where this sort of thing might be useful. So what we do is kind of going like 0.3 for the alpha. So mostly sparse with a fair bit of dense. And we get these. So we get soft purple topware. And I think it doesn't, like the purple isn't really coming into this very much. So what we can do is, you know, if we look very quickly at the data above, we saw that there was, in here, we have this base color parameter. So maybe we can actually filter for the color as well. All right, so we're doing a hybrid multimodal search, but we're also adding in metadata to this now, right? So you could do like a named entity recognition to pull out a particular color or something, or even the type of apparel, and then you could apply that to your filter using Pinecone's metadata filtering there. And then like straight away, you get pretty cool results. So let's try another one. This is near the end now. You're getting bored of me going through code. So here we have soft green color topware. We do the same thing. We're searching for the base color of green, and we get all these results. Now, argue like in the actual metadata for these images, it literally says they are green. even though I'm sure that is blue. But that's the data spot. So it is pulling in what the data set is telling us is green. So that's the code or the example walkthrough. Switch back to the slides, and I think, yeah. So what I'll do is I'll hand over to Amanda, and we'll go through the Q&A.
Okie dokie. Yeah, we have a lot of questions, so we're going to try to get to as many as possible. By the way, I really feel like shopping now after that. So thanks, James. But before we dive into the questions, I'm going to call Sebastian on. And Sebastian, will you introduce yourself to folks real quick?
Of course. Thanks, Amanda. So I'm Sebastian Bruch. I'm a staff research scientist at Pinecone. And I do research on information retrieval, vector search, yeah.
Great. So Sebastian will be helping us tackle some of your excellent questions. So let's jump on in. Do you have recommendations on the best embedding services to use for dense vectors or sparse vectors? Any guidance around that?
James, did you?
Sorry, go ahead.
You need like a buzzer.
I can. Well, there are. So I can speak to the sparse vector embeddings maybe first. I suppose there are a few models that you could use in addition to BM25, which is a purely lexical model. There is this effort to bring deep learning into learning sparse representations for text. And you can, and there are open source models available that you can use, much like a dense model, to embed your data. One of them being SPLADE, another being Unicoil. And so these essentially produce sparse vectors, much like BM25. However, in addition to learning weights or importance weights for your terms in the document, they also do other clever things like expansion. So they add synonyms to that are relevant to your document, or other concepts that are related to the topic of the document. They encode that into the sparse vector, so you have a richer representation that is learned. James, do you want to add anything to that?
Yeah, I think that the SPLADE recommendation is very good. As for the best embedding services to use for those dense and sparse. So if you are going to, if you're going to go out there and look for SPLADE, you can find it on Hugging Face, Transformers, and there's also a SPLADE library that you can use. So either of those, and then for dense vectors, you have a ton of options. So you can use Hugging Face Transformers for the open source stuff. If you want to use like a API-based service, you can go like OpenAI or Cohere. They both do pretty good embedding models as well.
Great, thank you. Can sparse vectors help with similar term matching? Example, let's say the query includes the word company, and we want to pull up documents that have words similar to the keyword company, institute, business, corporation, establishment, office, as other options.
I can jump. I'll if you want to say anything, Sebastian, please do. But so the SPLADE model that Sebastian just described is actually very good for this. So it is as I understand it, and Sebastian will probably be able to explain better, in the past, what you would have to do is kind of hand write a load of rules in order to do this. So BM25 and stuff, you would have to then kind of add these rules in manually. What SPLADE does is it basically learns them from just looking at tons and tons of language data. So kind of had a visual somewhere that described it, but I can't find it. So you can use SPLADE to do that, basically.
Great, thank you. Would a message in a conversation be an example of a sparse item message in a bigger context, the conversation? For example, in my chat bot, I need to match input message to where else in the conversation we may have talked about this subject, where I have been creating embeddings for every single message and response separately so far.
What a message, I'm just trying to figure out conversation, bigger context. So I don't think the message would be, as far as I'm aware, the message would not be a sparse item. So I think what you've been doing is you've been creating embeddings for every message and response separately so far. Like that's the way that I would do it. I don't know if there is a better way of doing it. So yeah, I'm not sure. I don't know if there is a way of creating like a sparse embedding for a specific message in relation to your broader conversation, as far as I'm aware.
Our question asker thanks you in the chat, and it confirms that it's a decent way. So there's some validation there, I think. Now Chris has a question about speed. Speed tends to come up a bit in these questions. So how is the speed impacted on returning results? I work with news data, and it's very important that it is fast.
So I guess I can take this question perhaps, but I would say in general, it depends on a number of factors. One being the sparsity rate of your vectors. I assume this question is targeted at sparse-dense, not just simply dense. But if your vectors have very few non-zero coordinates or terms, then typically, obviously, it is faster to perform retrieval on that. But if your vectors are denser, that is, you have a lot more non-zero terms in your vectors, that obviously affects the speed. It depends on the sparsity of the query itself too. So typically there's the sparsity of documents and queries. That sparsity rate is asymmetric, meaning that queries could be much shorter than document vectors. But in some cases, queries could be very long, and obviously that affects performance as well. Additionally, it depends on, I guess maybe I shouldn't get into too much into the technical details, but the balance between the weight that you give to the dense vectors versus sparse vectors, it also affects performance. If you insist on retrieving results that are more relevant based on the dense component, then the sparse index or the sparse part of the index doesn't have to work as hard to fetch the relevant documents, the top K documents. I hope that kind of give you an idea of what you can expect. You can try it today and see if it's okay for your use case. But there's no one single number that I can say is sort of the speed that you should expect. It really depends on your use case.
I wonder is another component of this that isn't necessarily in the question, but like if your news data, I imagine part of this is just going to be adding the news data to your database and making sure that it is that people searching for it are going to see in the results like immediately. So that is probably also an important factor, and for that you basically need a vector database that's going to refresh your index very quickly. So at least within Pinecone, we have 2 indexes that can do that very quickly, which is P1 and S1. And I think even P2 is relatively quick with this. But P1 and S1 in particular, you can add like 1 million new vectors. So it's like you could add 1 million new news stories to your database, and the results for those stories will appear like basically immediately. I think the actual number is something like crazy, like 300 milliseconds later or something. But for all intents and purposes, I think it's practically immediate, which is just another component. It's not necessarily separate to what Sebastian was going through.
Great, thank you. And you guys are receiving some thank you love in the chat from Chris. So it's like a conversation. It's great. So another question: do you know what is a performance impact? What is a performance impact when you combine these dense and sparse vectors? If vector length is very long, this may affect a performance by large margin to calculate dot product / cosine similarity.
I think I partly answered this question, yeah. But James, did you want to add anything to that?
No, I think you covered it well.
And do you use something like dense lexical representations, DLRs, to get dense vector for sparse one?
That's so meta. No, we don't. We actually do retrieval over the sparse vectors, or rather, I should say hybrid vectors.
We have a question from Robin. What is the roadmap for building more advanced operations on vectors from multiple databases? For instance, I may want to have a weighted sum of sparse/dense metric scores. One option to implement this would be, for instance, to append sparse and dense vectors into one long vector, then perform a weighted elucid distance, performing the computation on the vectors immediately in the database is advantageous, as it means I don't have to return all scores of all items, form all databases from the API, add locally, and re-rank to get the best N. Is this possible in the future? In this example, I can't first weight the vectors and then upsert because the weighting is done in real time to enable real-time personalization. Now that's a hefty one, so I'm going to give you guys a second to relook at it in the actual Q&A, and yeah, take it away.
So I'm not sure. Sebastian, do you have any ideas?
So if I understand the question correctly, you have sparse and dense components that you would like to weight in real time depending on the query itself. And you don't want to do that during upsert. And in fact, that's the behavior that you can expect today from Pinecone. So when you upsert your vectors, you upsert dense and sparse vectors together. And it is only at query time that you can kind of weight the sparse versus, or balance that trade-off, how important sparse is versus dense, by encoding that weight into your query. So think of a dot product, which is an additive function. So dot product of a hybrid vector with your hybrid query vector is just the dot product of the dense parts plus dot product of the sparse parts. And so by weighting your query's dense part versus sparse, you can kind of balance how much importance you're giving to your dense results versus sparse results. I don't know if that answered your question.
They also added in the chat, what about more than 2 vectors? And sparse, sparse, or sparse 2 times and dense?
I don't know if they have that on our roadmap, but perhaps I can offer an alternative. If you have 2 sparse vectors that you need to search over, that is, you have 2 documents with 2 sparse components, you can always concatenate them into 1 sparse vector, if that makes sense.
Great, thank you. How does sparse-dense retrieval differ from SPLADE v2 embeddings?
So, I mean, I think they can, at least from what I have, and maybe Sebastian probably want to add to this, but from what I have seen and testing these is that depending on what the models are good at, there can actually be very little difference. So you can basically, you can take a dense embedding model, and also for your sparse vectors, use SPLADE embeddings, and the performance of using like pure SPLADE versus a mix of both is actually pretty much the same. Because SPLADE is very good, and it has that sort of learning component. So you can kind of, at least the way that I think of it, and maybe Sebastian will want to correct me, is I think of SPLADE as, yes, it creates sparse embeddings, but it kind of acts kind of like a dense embedding model in that it manages to pull in the meaning to some degree. Yeah, I don't know if there's a better way of describing that, Sebastian.
I agree with that. So I would add that SPLADE is just one model that produces sparse embeddings for documents, for text documents. However, the concept of sparse-dense retrieval is more general than that. So you can imagine encoding your text with a SPLADE model into a sparse vector, and images using the clip model into a dense vector. And now you can perform multimodal search over texts and images. And so in that way, the Pinecone index supports that use case, which is not mutually exclusive with like SPLADE necessarily.
Perfect. So Kirk couldn't tell from the demo what the speed differences between sparse and dense queries.
I'd refer you to the performance numbers that we publish for specific pods, because that's the latency that you can expect. But as I said, it very much depends on your use case.
Perfect. Does Pinecone use an inverted index for sparse and a graph-based index like HNSW for ANN? If so, are the candidates retrieved independently and combined based on this alpha parameter?
The short answer is no. We have our own proprietary index and retrieval algorithm. So yeah.
How exactly does the alpha parameter affect the results set? Is it taking a weighted score from the sparse model ranking and the dense model ranking?
So if we, so I think Sebastian kind of mentioned earlier that the dot product is additive, and I'm just kind of trying to re-say what he said. I'm not sure if it's the best way of describing it, but essentially, if you look here, you're taking your dense vector, you're taking a sparse vector, and you are, where is it, here, right? So if your alpha value is 0, basically the sparse values are all going to be maximized. They're going to be their normal values, whereas the dense values will go to 0, right? So that basically means when you're comparing everything with dot product, the dense scores, because you're using dot product, are going to be 0, I think it is. So the dense part is basically not considered in that search, or the dense score. Whereas on the other side, right? So if you have an alpha value of 1, it means you're making your sparse values 0. So then the score from them is going to be lower, and it's going to maximize the scores between dense embeddings, if that makes sense. Sebastian, if there's a better way, please go ahead and do that.
That makes sense to me.
Okay. Go ahead and do that, said James. Now we're almost hitting time, so we're only going to cover a few more questions. And so Kazim wants to know, can you explain how dense and sparse vectors get combined at the query time? Also, for what type of queries / docs you see hybrid search outperforming dense search for text?
Sorry, James, go ahead.
Okay. So for the, okay, I'll go for the second part, and then I'll let you do the first. So for the types of queries and docs that you see hybrid search outperforming dense search at text, like one big use case for this is, well, one, actually what you saw, so the multimodal thing is a pretty good approach for using this, like considering multiple modalities. But another one is where you have, let's say you have your dense embedding model, but it hasn't necessarily been trained or doesn't perform well on your data set because your data set is different to the data set that model was trained on. So that means that your target data set is out of domain. And this is where dense embedding models don't perform so well, so they don't generalize very well. And it's where sparse embedding methods do tend to perform better. And that's the sort of use case where you maybe you want to go with hybrid search. And then obviously the earlier one, I think we missed a part of the question. Can you explain how dense and sparse vectors get combined at the query time? Is that something you could go through, Sebastian?
I think very briefly, I just say that you can think of a Pinecone, thinks of your vectors, whether they're dense, sparse, or hybrid, as vectors. And it directly computes finds the top K according to maximal dot product. So there's conceptually, there's no difference between a hybrid vector and a dense vector. I hope that answers your question.
Great, and we'll do one last question. Would pre-processing your query for entry recognition influence sparse-dense search?
So for the query, I'm not sure exactly in what way you mean, but I think at one point I suggested you could use named entity recognition in order to extract a a metadata item and filter based on that. In that case, and this kind of also answers Bill's question, which is next. In that case, metadata filtering in Pinecone actually reduces, in most cases, vast majority of use cases, reduces the search time, so it makes it faster because you're kind of searching through a smaller space. At least I know that's the case with P1 and S1. I'm not sure about the other pod types.
Okay. Well, on that note, it is officially 1:01. So we are going to close up. Thank you all so much for joining us. A big round of applause for James and Sebastian. I was like the theatrical element at the end. And again, if you guys have continued questions, you can reach out to me personally, and I will get your questions answered. You can reach me at amanda@pinecone.io. And yeah, thank you again. Thanks, everybody. Have a good one.
Thank you. Bye.